to 4% of our DNA from Neanderthals, and that 100% of us may have 100% of our DNA from outer space. No joke. At least the biochemistry that defined the coding system of your DNA may have happened off-world, and perhaps even long before Earth existed. Life is the coolest thing to have happened in our universe. It would be nice to know if it happened anywhere else besides Earth. If nothing else, to know just how badly we're screwing up as we flirt with self-extinction. But not only have we never found credible evidence of life on or from other worlds, we only have the sketchiest of ideas of how it began on Earth. Makes it pretty difficult to say much about what's happening out there. But one encouraging detail is just how quickly life got started on Earth. The earliest fossils are dated to within a few hundred millions of years after Earth first cooled from its early molten hellball phase. And if you believe some of the more tentative biosignatures, it could be much earlier. In fact, life got started so quickly on Earth that some have argued that natural selection just didn't have the time to take raw elements all the way to the first single-celled life form. This difficulty has led some scientists to propose panspermia, the idea that life did not start on Earth at all, but rather travelled here in the form of extremely simple and presumably extremely robust organisms. It's a fun story and we've talked about it before, but it's not supported by evidence and generally not considered particularly likely. But there is a middle road. Perhaps life didn't start in space, but maybe its building blocks did. Pseudo-panspermia is the idea that many of the complex molecules critical for abiogenesis, the formation of life, were not formed on Earth, but rather in the depths of space, in some cases long before the formation of Earth itself. If these then rained down on our planet in its early years, that would allow our molecular ancestors to skip many of the steps in their path to the first cell. The evidence for pseudo-panspermia is rather strong, and the most compelling of that evidence is just in, with the safe return of Osiris Rex. But before we get to those results, let's review what little we know about the first formation of life. Life as we know it is based on a complex interplay of organic molecules, primarily nucleic acids, proteins, lipids, and carbohydrates. In your body, these work together to form the intricate machinery of the modern eukaryotic cell. Of course, the first life was much simpler, and life's precursor simpler still. For example, self-replicating RNA molecules of the RNA world hypothesis. But how did a bunch of non-living chemicals even get to something as complex as RNA? Extremely broadly, we assume that there was some energy and chemical-rich primordial soup where simple elements combined into organic molecules, then combined and recombined in a chain of trial and error until this natural laboratory first stumbled on a self-catalyzing and then self-replicating molecule. The step from organic molecules to complex self-replicating RNA is still mysterious, even if there have been recent advances. But the pre-RNA part of the story, we've known that's possible for decades. Back in 1952, a pair of scientists attempted to replicate the conditions of the early Earth, with a liquid water ocean evaporating into an atmosphere of hydrogen, methane, and ammonia. An electrical spark simulated primordial lightning, powering a chain of reactions that ultimately led to a variety of organic compounds, including 5 amino acids, the building blocks of proteins. This was the famous Miller-Urey experiment, and it was our first hint at how the seeds of life may have formed. That experiment has now been repeated in a variety of ways, and we now know that amino acids can spontaneously form given the right raw materials, an aqueous environment, and an energy gradient. The apparent ease with which amino acids form has led scientists to wonder just how ubiquitous these organic molecules might be, not just on Earth, but through the universe. For example, in the chunks of rock and ice that rained down on the early Earth, first building our planet and then perhaps seeding it with the precursors to life. One of the first pieces of evidence that space rocks are packed with organic compounds was the Murchison meteorite, which fell in Australia in 1969. This is a carbonaceous chondrite meteorite, so mostly made of carbon, clay minerals and water, but it was also found to contain over 90 different amino acids, including some that are not commonly found on Earth, as well as the nucleobases purine and pyrimidine, which are critical components of DNA and RNA and other organic molecules. Carbon dating estimates that Murchison is around 7 billion years old, so a couple of billion years older than even our Sun, meaning that complex organic chemistry would have been occurring in space long before life ever emerged on Earth. It's hard to be 100% certain about the origin of the molecules found in the Murchison. However, the amino acids in this meteorite had one distinct difference to those typically found on Earth. They came in both left and right-handed varieties, both chiralities, both mirror reflections. But all amino acids produced by Earth life are left-handed, a chirality that's been locked in since the first common DNA or RNA ancestor of all life won that great molecular war 3.5 to 4 billion years ago. The presence of both chiralities in the Murchison meteor tells us that these amino acids had an abiotic origin, supporting their pre-life formation. Pretty convincing? But the best way to be sure there's no cross-contamination from earthly life is to get samples directly from space. And there have been some incredible efforts to do this. NASA's Stardust mission collected samples from the coma of Comet Wild 2 and returned them to Earth. The Japanese Space Agency was the first to land on an asteroid and return samples, twice actually, with Hayabusa and Hayabusa 2. And ESA's Rosetta mission was the first to send a lander to a comet where it analysed samples on location. These and other missions have shown that organic compounds are abundant on space rocks. But how far along can this prebiotic biochemistry really advance in space? How much of a head start might pseudopanspermia have given to life on Earth? Some of this has now been answered by NASA's OSIRIS-REx mission. In our long tradition of unwieldy science acronyms, this stands for Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. The spacecraft launched in 2016 with its sights on an asteroid by the name of Bennu. Bennu is a pretty ordinary carbonaceous asteroid of middling size at around 500 meters in diameter, is part of the Apollo group, a collection of more than 20,000 asteroids with orbits that cross Earth's. That means they do sometimes slam into our planet, like the one that exploded over Chelyabinsk in 2013, or as in 2024 YR4, which has a minuscule chance of hitting Earth in 2032. Bennu has no immediate chance of hitting us, but it does make a close approach to Earth of around 300,000 kilometers or 24 Earth diameters every 6 years. The upside of these potentially cataclysmic neighbours is that they're quite easy to visit, which OSIRIS-REx did. It started that journey in orbiting around the Earth, followed by a mad dash to catch up and orbit the asteroid. Then after a few years of observation and analysis, a suitable landing site was identified and the spacecraft touched down. Samples were collected before an easy escape from Bennu's frankly pathetic excuse for a gravitational field. OSIRIS-REx rejoined Earth's solar orbit and dropped its sample capsule into our atmosphere in September of 2023. And after all of that, the capsule's parachute failed. Its first parachute failed, the second opened just fine, and the capsule landed right on target in Utah. Since then, scientists have been hard at work analysing the sample, and the first results of the findings were finally published in January this year. So, what did we find? Among the most exciting discoveries in the sample are all 5 of the nucleobases that serve as the code for DNA and RNA. This is the first time we've found all 5 on the same space rock. The samples also contained 14 of the 20 amino acids that life on Earth harnesses to make proteins. These amino acids have both left and right-handed chirality, just like the Murchison molecules. The Bennu sample has various other interesting compounds, including a surprising richness of ammonia, 12 times higher than in the Murchison meteorite. Curiously, Bennu orbits too close to the Sun to preserve pure ammonia, so that richness hints at a colder, more distant origin, but more on that later. One of the most exciting finds were 11 different minerals that we know form when brines slowly evaporate. That means Bennu, or the stuff that formed it, was once in an aqueous, salty environment. In fact, there were many signs of the role of water in Bennu's formation. Its minerals match most of the water-altered meteorites ever found on Earth, as well as the samples collected from the asteroid by JAXA. But unlike most meteorite samples, Bennu contains sodium-rich salts, which are rare in meteorites. Similar salts are found here on Earth, like in Searles Lake, California, confirming that Bennu once contained pockets of sodium-rich water. But normally we don't find those sodium-rich salts in meteorites because they react strongly with our atmosphere. But because Bennu's samples were stored in pure nitrogen, they maintained a pristine suite of salts for analysis. And with this analysis in, we're able to reconstruct a likely origin story for this asteroid. And that origin is probably a water-rich world that existed for a time in the early solar system, but has since been destroyed. Let me take you back 4.5 billion years ago to the icy fringes of the early solar system beyond Jupiter's orbit. A distant protoplanet is forming from a mixture of rock, metal, and frozen water. As radioactive elements created in an ancient supernova decay within, heat melts some of the ice, creating mineral-rich reservoirs. These ancient waters interact with ammonia and formaldehyde, sparking the formation of complex organic molecules. When the water eventually evaporates, it leaves behind veins of brine-sourced minerals. This protoplanet, however, is doomed. Before it can grow to full planethood, a catastrophic collision, perhaps with a similar body, scatters its fragments into space. And Bennu and many other asteroids pull themselves together from this debris. In the unsettled early solar system with its wandering gas giants, Bennu's orbit was also fated to wander. Eventually, it settles into an orbit perilously close to an inner solar system planet. A planet that would slowly turn blue-green and then twinkle with night lights, and then send a tiny visitor of metal and silicon named OSIRIS-REx. Or at least, it seems like this is the most likely story, based on the bits of Bennu that we brought back home. And if Bennu has the variety of organic compounds that we discovered, so do many asteroids, and probably comets. Many of these peppered the early Earth, far more than today. In fact, they are kind of what the Earth is made of. Like I said, pseudopanspermia, the idea that the chemistry of life got a head start from space molecules, is pretty well supported. But does this tell us anything about the likelihood of life elsewhere? We can be pretty sure that there are watery worlds out there that started out with an abundance of organic compounds, all the way up to amino acids and even nucleotides. It's becoming harder to imagine that simple life doesn't form in lots of places. But the observation of DNA and RNA coding nucleobases could tell us something pretty profound. If all planets start with a similar chemical cocktail, maybe there's a pretty narrow path to life everywhere, one that involves DNA-like molecules. Maybe the system that codes Earth life, including your own DNA, was set by extraterrestrial biochemistry. And what about OSIRIS-REx? It delivered its sample, but it stayed out there to continue its adventure. NASA has renamed it OSIRIS-APEX, and is now preparing to intercept the asteroid Apophis. This time, the mission isn't primarily to discover the origin of life, but to help prevent its annihilation. Apophis is one of the most hazardous Apollo asteroids. it has a minuscule chance of hitting Earth in 2036. OSIRIS-REx will study any changes to the asteroid that occurred during its close encounter with Earth in 2029. This will help us track Apophis more precisely. It'll also teach us more about these close encounters, perhaps allowing us to avert a future giant impact. Well, thanks for looking out for us, little buddy, and for helping us seek our chemical origins in a protoplanetary and perhaps pre-solar space-time.